All right, last thing I'm going to talk about, urbanization. We as humans have become an urbanized society. In fact, as of 2007, for the first time in history, more people have lived in cities than in rural areas. Today, it's around 54%. By 2050, the United Nations projects it'll be around 68%. So in essence, as time is going on, we are becoming a more and more urbanized society. That's not surprising. People are living in cities, cities are growing, and while that isn't as critical as things such as cattle farming, that still has some pretty major consequences to it. So what I wanted to devote this last video to is kind of talking about some of the other consequences of that, and then trying to tie some of it back into how these things actually affect the carbon cycle. So there are problems with this. We've already talked about some of this. Urbanization requires deforestation, which that removes a carbon sink. It requires a lot of concrete. Concrete itself actually is based on fossil fuel. And so creating concrete has a carbon footprint to it. And then a lot of urban sprawling. I know, I'm recording this during a pandemic. I don't know how much longer this pandemic's going to last. I'm hoping I can use this video for at least a while. That being said, pre-pandemic, and I would assume post-pandemic, well, especially now with telecommuting, there's going to be a lot more sprawling happening. Cities are stretching beyond their limits. People who work in San Francisco oftentimes don't live in San Francisco. They live in Marin. They live in San Rafael. They live in Sonoma. They live in Santa Rosa, areas that are further away. Or they live in Tracy or Livermore, or they live in Gilroy or Hollister. I've even seen an ad for people who live in Silicon Valley, or so people who work in Silicon Valley, to live in Los Baños. If you know where that is about a 2-hour drive. That's about 70 miles away from the Bay Area, and yet people do that. That requires more transportation, which means more roads, which also means more cars, which also means more carbon dioxide emissions. And these things have consequences. Urban areas use heat very differently than non-urban areas. That changes Earth's surface energy balance. That changes the urban heat island effect, which we're going to talk about towards the end of class today, or towards the end of this video, essentially towards the end of class today. Increased pollution, and therefore increased greenhouse gas emissions. So let's talk about these things really quickly. So first off, let's talk about how the surface of the Earth uses energy. So if you remember from a few weeks ago, of all the energy we get from the sun, approximately 51% of it is absorbed by land. 4% of it is reflected off of the land. However, different land covers treat sunlight differently. If there's snow on the ground, that snow is going to result in more reflection and less absorption. On the other hand, if you have a big black tar surface, that's going to decrease the amount of reflection and increase the amount of absorption. You get two very different results in that case. So land use changes greatly affect Earth's surface energy budget. And if you remember, Earth's surface energy budget is balanced. So by changing Earth's surface energy budget, we are throwing Earth's surface energy budget off of its balance, and therefore resulting in other things having to change as well. Other things having to change as well. Now, this next image, this is actually an image from my master's thesis. So if you pull your hair out, don't worry, I'll actually walk through each of these components very briefly. But then I very briefly want to talk about how urbanization has changed them. So here we go. I know. Ah! Don't worry, it's not that bad. All right, so let's actually talk about it. Okay. So we have this little equation down here. And here's what this equation actually represents. These two things right here actually represent energy in. This right here, this S sub D, this is energy in from the sun. This LD represents energy that's actually re-emitted from clouds or from gases in the atmosphere that return back to the surface of the earth. This alpha right here, this actually represents albedo. So the amount of energy absorbed by the surface, or the amount of sunlight absorbed by the surface, would be equal to 1 minus the albedo times that amount of energy that hits the surface. So these two things represent our incoming. This right here represents the amount of radiation that the Earth emits. If you remember from the Stefan Boltzmann law, the warmer an object is, the more radiation it emits. That's what this right here represents. These other three things all represent different components of Earth's surface that use energy. This H right here is what's called sensible heat. If you remember, I talked about conduction and convection and how those things actually heat up our atmosphere. That's that. This LE right here represents latent heat. This is heat that's absorbed or released by water as it changes phases. So if you've ever seen moisture condense or dew forming on the ground, that actually exchanges heat with the atmosphere. So that's what that is. And then finally, some heat actually gets absorbed by the ground itself. That's this guy right here. And the concept is this all here, all of these negatives, this represents energy out. So the idea here is that energy in minus energy out equals 0. That is a balanced budget. Income minus outgoing equals 0. That is a balanced budget. Well, now let's actually talk a little bit about this. So let's suppose that the surface of the earth is covered in snow. This albedo right here is going to be really high. That means that we're actually going to get less radiation absorbed by the surface of the earth. In order to account for that, these four things are going to have to decrease as well. Very likely the biggest decrease is going to be in the temperature of the surface of the earth, and then balance is re-achieved. Now let's say we clear out all that snow and pave down a parking lot. Now what we've actually done is we have decreased our albedo. That increases the total amount of radiation that hits the surface of the earth, or that is absorbed by the surface of the earth. What that actually does is that forces these other things to increase to make up for the change. On the other hand, if we clear out all of the trees, all of the plants, all of the trees, all of that kind of stuff, that can actually significantly change how much latent heat is absorbed by the atmosphere. So that can decrease this, which then forces these other things to increase to pick up the slack. All of that being said, when humans come into the picture, they are actually going to change at least the values, the numbers of these different components of this equation. Now, once again, I could teach a whole lesson on just this equation. And in fact, I wrote a whole master's thesis on just this equation. So I don't expect you to become an expert on it. What I do want you to know is that in order to maintain Earth's surface energy balance, if humans change one thing, that forces something else to change. That changes everything. So what have humans changed? Well, the first thing we've changed is we have actually decreased the average albedo of our cities. If you look outside, if you are living in a city right now and you look outside, you'll notice a lot of gray, blacktop covered surfaces. Those surfaces are less reflective than natural soils or plants. They are just less reflective. Therefore, more heat is being absorbed and retained by those surfaces. In order to counterbalance that, temperatures need to go up. So that's the first thing. The next thing, if we have warmer temperatures, if our ground is warmer, that means there's going to be more conduction and convection, which means a warmer atmosphere. Second thing, if we actually remove plants, that increases albedo of pastures. Actually remove forests. Forests are typically very dark. If we remove them and replace them with things such as pastures or grasslands, that actually increases albedo. Other things, removing vegetation, that can also change the amount of that can actually change the amount of evapotranspiration, basically the breathing and sweating of plants. And that changes latent heat energy. That actually results in less latent heat being absorbed by these things, which now means there's more heat in the atmosphere, resulting in a warmer atmosphere. All of these components are changed by humans. So we as humans are throwing our energy budget off of balance. But unlike the best state and federal governments in the world, our Earth system knows how to run a balanced budget. So other things change to make up for that. One of the biggest changes that happens in urbanization is what is referred to as the urban heat island effect. So most urban centers are made of concrete, asphalt, bricks, and lower albedo surfaces compared to things such as grasslands or trees. And as a result, cities actually become warm. This is what is referred to as the urban heat island effect. So here's basically what happens. By removing vegetation and replacing it with darker surfaces, we've increased the amount of heat that our cities are absorbing. By increasing the amount of heat that our cities are absorbing, we're making them warmer. We're making them warmer. And then the end result, cities can be as much as 5 to 10 degrees warmer than surrounding rural areas. They could be as much as 5 to 10 degrees warmer than surrounding rural areas. And this is something that we actually see on a regular basis. So this is just like a textbook image right here that shows that surrounding non-urban areas, surrounding rural areas, farmlands, even suburbs are a little bit cooler than downtown regions, which are much denser and have a lot more heat in them. But we actually don't even need to just look at some textbook graphic. I can actually show you this in actual observations. So this is a plot that my old thesis advisor made. And so I want to give credit to her. I wrote her name down here on the bottom. And so here's what this is. Up here, this image actually represents land cover, the different land covers of different locations. Wherever you see red, that represents urban centers. Here's San Jose, the Peninsula urban area, the East Bay, Livermore over here, then here's Altamont Pass, here's Tracy. Up here, this is Antioch. Up here, this is Solano County. Over here, this is the popular tourist attraction of Stockton, California's favorite city, the city that everybody goes to. Up here is the city of Sacramento. Up here is the city of Chico, home of Sierra Nevada Brewing Company. Drink a torpedo for me if you're over 21. Well, let's actually take a look at this other image. This is actually observed temperatures at 8 p.m. on May 9th, 2011. The urban heat island effect actually has its biggest impact at night, right after sunset. So 8 p.m. in May, that's right after sunset. That's maybe 30 minutes after sunset. Wherever you see yellows or brighter colored greens, those represent warmer temperatures. Wherever you see darker greens and blues, those represent cooler temperatures. Well, here's San Jose. Here's the East Bay. Oops. Here's Sacramento. Here's Stockton. Take a look at that. Some of the big urban centers are indeed warmer than the surrounding non-urban centers, even those that are at just about the same elevation. Even those that are just about the same elevation, like the areas outside of Stockton, aren't really higher in elevation or lower in elevation, and yet they're cooler. So we actually do see this impact. Okay, Terrence, it's a little bit hotter in cities. What does that matter? Well, I don't know about you. Maybe it's not that big of an issue here in California, but let's say you live in a city like Dallas, Texas. Dallas, Texas gets really, really hot in the summertime. If it is warmer by 5 to 10 degrees in Dallas than it is in the cities surrounding Dallas, guess what that means? That means in order to cool your house at the same temperature, you need to use more air conditioning. Well, in order to use more air conditioning, guess what? You have to use more electricity. To use more electricity, you have to burn more fossil fuels. That is why the urban heat island has a carbon footprint, and that is its component to the carbon cycle. So this does go full circle back to where I started at in this module. Now, that being said, what are some things that we can do about this? There's a few things that we can do. First off, more parks, more trees, more higher albedo surfaces. Obviously, we can't paint our roads white because white is very, very bright and reflective. That would blind you. It'd make it really hard for you to drive. Lots of accidents. That'd be bad. Don't want that. What we can do, though, is we can brighten up the surfaces of things surrounding the roads. That could result in, at least to some extent, a higher albedo and therefore a little bit cooler. That's the obvious stuff. The less obvious stuff, things like green roofs. There are a lot of roofs that have nothing on top of them, or they're just gray. What if we cover them instead with parks? Now you have a nice little picnic area that you can go to at the end of the day. That's good. What about higher reflective roofs? If you don't live in a flight path, and therefore a big beam of white isn't going to have any impact on any approaching planes, if you actually change the color of your roof from black to white, that can greatly increase your albedo. That can greatly decrease the amount of heat that your house is absorbing. That can lower energy costs. Public transportation is another thing. If we create a society that's more reliant on public transportation, one, means that there's less need for roads. Two, that also means there's less cars on the road, therefore there's less carbon dioxide emissions that way. So those are just a few solutions. And actually changing changing the color of your roof, if you have the ability to do it. Now, I'm not saying that everybody has the ability to do this. I live in an apartment. I don't have the ability to do this. But even just changing the color of your roof can greatly change how hot your house gets. And if you change how hot your house gets, you can change how much energy you need to cool your house down. This can result in much, much, much less energy being used for air conditioning. Once again, that's more money in your pocket. For states like California, which have a very heavy renewable energy portfolio, that also means that we now rely less on burning of fossil fuels because we don't need them. We reach a point where our solar infrastructure, our wind infrastructure, our geothermal infrastructure are good enough. So that's one step that you can take. And this doesn't even necessarily mean that you have to spend thousands and thousands of dollars getting your roof redone. You can even just get a decent tarp and cover your roof like that, as long as it's legal and you don't live in an HOA area and as long as it looks good, you could probably do that. That being said, that's it for this module. The next module, we're actually going to be talking a little bit about some of the natural causes of climate change and also how our planet is responding to our warming via processes called feedbacks. I mentioned a negative feedback earlier in the class. I'm going to be talking a lot more about negative and positive feedbacks for next time. So that's it for today. If you have questions, comments, concerns, as always, please don't hesitate to reach out to me. I know this is a lot of stuff, but thank you for watching.